In this video, we're going to learn about ionic compounds, and we'll learn the properties of ionic compounds and how they compare to molecular compounds, and we'll figure out how ionic compounds form into crystal structures. So first of all, a bit of a reminder about chemical formula. So remember, chemical formulas identify the elements involved and the number of atoms present in a compound. And for these examples, the atom or the ion with the lower electronegativity would be recorded first, which would be followed by the atom or ion with the higher electronegativity. So in this example, in the example of ionic compounds, the metals will always have a lower electronegativity than the non-metal that it combines with. So you always write the metal ion first. That is something that we learned in grade 10. Always write the metal first. The reason why is because it has the lower electronegativity. So now we'll go over the crossover rule, how to come up with the chemical formula. So this is review from grade 10 science, but I thought it was worth reviewing. So the first thing you do is you write the unbalanced formula first, putting the lower electronegativity ion first, so the metal first. Then step 2, you would write the valence, or the charge, above each atom or ion. And then you'll cross the numbers over to the subscript position. Remove any subscripts of 1. You don't need to record 1. And then, if needed, you'll reduce it down to lowest terms. So for ionic compounds, we do reduce down to lowest terms. Remember, for molecular formulas, we don't. And then remember that polyatomic ions are treated as a whole package. So if you need to bring down a subscript, you'll put that into brackets and then bring the subscript down outside of the bracket. So we'll do some practice with that. So our first example is magnesium oxide. So first we'll write the symbols. So Mg and O. And we look up the charges. Magnesium gets a charge of 2 plus. Oxygen has a charge of 2 minus. So we'll cross those over. So we get Mg2O2. But actually it would just be MgO. The next one, calcium phosphate, we're dealing with a polyatomic ion here. So calcium and PO4. Calcium has a charge of 2 plus. Phosphate has a charge of 3 minus. So we're going to need to put brackets. I'd like to do that first. Then we bring down the charges like so. Rewrite it. So it's Ca3 brackets PO4 brackets 2. This one does not need to be reduced down because it's in its lowest terms. So that's how you do the crossover rule. So if we look at molecular versus ionic compounds state at room temperature are crystalline solids, whereas molecular compounds can be either solid, liquid, or gas. The melting point for ionic compounds is quite high. Molecular compounds would be lower. Ionic compounds, when you place them in solution, will be conductive. Molecular compounds will not. Ionic compounds are usually high solubility. Molecular compounds are usually low. And finally, the bonding between each is different. So with ionic compounds, there's a transfer of electrons from the metal to the non-metal. So there's not a sharing of electrons. It's actually a full transfer. Whereas molecular compounds share their electrons between the two nonmetals in their bond. We'll learn later that sharing isn't always equal, and that can lead to polar molecules, but that will be for another lesson. So in an earlier lesson, we learned about electronegativity, and that's the ability of an atom to take an electron from something else, so how much they want the electrons. So the difference between two atoms tells us the type of bond that will form. So you'll have to look at the two atoms that you're working with and then find the delta En, or the change in electronegativity. So if it's from 0 to 1.7, it forms a covalent bond. So we'll save those ones for a later lesson. If it's higher than 1.7, then it forms an ionic bond. So we'll also learn a little bit later, for covalent bonds, you can have a pure covalent bond. So that would be from 0 to 0.5. So the electrons are pretty much equally shared between each atom, but then a 0.5 to 1.7 would be a polar covalent bond. So one atom is actually hogging the electrons. And again, we'll talk about covalent bonds in a later lesson. We're concerned right now with ionic bonds. So now we'll practice with a couple of examples to figure out their delta ENs. So the first one, we're being asked to take a look at KF. So the electronegativity for potassium is, and we'll look that up in our data booklet, so 0.82, and the delta EN for fluorine is 3.98. So now we'll find the difference. So delta EN is equal to, and it doesn't matter which one you put first, I would put the larger one first so you get a positive number. So 3.98 minus 0.82. Plug that into our calculator. We get to delta EN of 3.16. So this will form an ionic bond. The next one, we're finding the delta EN for O2. So it's going to be equal to the following. So we'll look up the electronegativity for oxygen. It's 3.44, so also quite high. But then there's two oxygen atoms, so 3.44 minus 3.44 is equal to 0. So this one is a covalent bond, and because it's less than 0.5, it's a pure covalent bond. And that makes sense because you're joining together two of the same atoms together, so they're going to share the electrons equally. Neither one is going to have a greater pull because of the same type of atom. So remember, ionic compounds contain a metal and a nonmetal. So the metal will lose its valence electrons to the nonmetal, and then the now charged ions will attract one another through electrostatic attraction, which forms the bond. So if we look here, we have sodium has 1 electron, valence electron. Chlorine has 7 valence electrons, so it's just desperately looking for one more. So sodium will donate its 1 electron to chlorine. So we'll have 1 positive sodium and a negative chloride ion. So they're going to attract each other through electrostatic attraction to form NaCl. So we'll try a couple more examples. So we'll draw the Lewis structures for each. So sodium has 1 electron, 1 valence electron to donate. Oxygen has 6, so it's going to take an electron from sodium. But we haven't satisfied oxygen's needs, so we actually need to draw in another sodium to donate its other valence electron. So we're going to have 2 sodiums with a positive charge and your oxygen with a 2 minus charge, and this will form Na2O. Our next example will be a little trickier. So we've got magnesium, and it has 2 valence electrons, and phosphate, we can see that it wants 3. So if we put this in brackets, it must want something along these lines. So now we have to figure out, okay, if we do the crossover rule over here, so we have Mg2 plus, PO4, 3 minus. We need 3 magnesiums to balance out the 2 phosphorus or phosphates. So Mg, so we're going to draw 2 more of these. And we also need another phosphate, which must have an overall 5 valence electrons. So this one can give 2 electrons to make that one happy. This one's going to give 1 electron here and 1 over here. This one's going to give its 2 electrons to give yourself the Mg3PO4 2. So that's how you do that one. So now we'll talk about ionic structures. So ions, when they form compounds, they don't form compounds. Instead, they form crystalline solids called lattice structures, and they have distinct ratios of positive and negative ions. So we'll often call them compounds, but they're actually formula units. So if you take a look at sodium chloride, you can see that sodium always forms a lattice, one sodium to one chloride, and then it's joined to a chlorine, and that's joined to a sodium, and that's joined to a chlorine, and so on. So you go through that way. So that's how ionic compounds form. We've already addressed polyatomic ions before, but just as a recap, polyatomic ions are ions made of more than one atom, covalently bonded together, but then they'll form ionic bonds with other ions. So these carry an overall charge, usually a negative charge, but you'll find out that that's not always the case. Now, a list of polyatomic ions can be found in our Cognity textbook in section 4.1.2. They're not listed in the data booklet. There's a list that you need to be familiar with, so that list that's found in Cognity would include that list. So they would be ones we commonly use. So phosphate, carbonate, hydrogen carbonate, sulfate, hydroxide, ammonium, and that would be pretty much the list.